All right, let's take a look at section 12.3, Permutations and Combinations. In this section, we want to calculate the number of permutations of n objects taken r at a time and use the factorial notation to represent a number of permutations of a set of objects. Calculate the number of combinations of n objects taken r at a time and apply the theory of permutations and combinations to solve counting problems. Definition. A permutation is an ordering of distinct objects in a straight line. If we select r different objects from a set of n objects and arrange them in a straight line, this is called a permutation of n objects taken r at a time. The number of permutations of n objects taken r at a time is denoted by p of n and r. P reminds you of the word permutations. N is the number of objects from which you may select, and R is the number of objects that you are selecting. Example, how many permutations are there of the letters A, B, C, and D? Write the answer using the P of N, R notation. Solution, we write the letters A, B, C, and D in a line without repetition. So A, B, C, D, and B, C, A, D are two such permutations. The slot diagram indicates there are 4 ways to choose the first letter, 3 ways to choose the second letter because letters can't be repeated, 2 ways to choose the third letter because we've already used 2 of them, and 1 way to choose the last letter, giving us 4 times 3 times 2 times 1, or 24 possibilities. This can be written more succinctly as P of 4, 4, or P in choose R, 4 choose 4, equaling 24. The number of permutations of 4 objects taken 4 at a time. So P 4 choose 4 equals 24. How many permutations are there of the letters A, B, C, D, E, F, and G? If we take the letters 3 at a time, write the answer using the P in choose R notation. The slot diagram indicates there are 7 ways to choose the first letter, 6 ways to choose the second, because letters can't be repeated, and 5 ways to choose the third, giving us 7 times 6 times 5, or 210 possibilities. This can be written in permutation notation as P 7 choose 3 equals 210. P is the number of permutations, 7 is the number of objects, and 3 is the number taken at a time. So permutations of 7 objects taken 3 at a time. If n is factorial notation, if n is a counting number, the symbol n exclamation point, called n factorial, stands for the product n times n minus 1 times n minus 2 times n minus 3 times times 2 times 1, where n exclamation point is read n factorial. We define 0 factorial to be 1. 6 factorial, for example, is 6 times every number less than it, every whole number less than it. So 6 times 5 times 4 times 3 times 2 times 1 is 6 factorial, which equals 720. Compute 8 minus 3 factorial. We work inside the parentheses first, order matters. So 8 minus 3 is 5, so this is 5 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. Compute 8 factorial divided by 5 factorial, which is also being divided by 3 factorial. Solution, we write out the factorials and then cancel. So 8 factorial is 8 times 7, 6, 5, 4, 3, 2, 1. 5 factorial in the denominator is 5 times 4 times 3 times 2 times 1. And 3 factorial is times 3 times 2 times 1. Now they've highlighted their cancellations. The 5 factorial in the numerator and denominator cancel. And then 3 factorial equals 6 and cancels with the above. So you get 8 times 7, which is 56. Compute the formula for computing permutation in choose R. Permutation in choose R equals the n factorial divided by n minus r factorial. So the quantity of n minus r factorial. Example, the 12-person theater group wishes to select one person to direct a play, a second to supervise the music, and a third to handle publicity, tickets, and other administrative details. In how many ways can the group fill these positions? This is a permutation of selecting 3 people from 12. So we have permutation 12 choose 3, which is 12 factorial divided by the quantity of 12 minus 3 factorial. And to solve this, we write out, first we tell ourselves that 12 minus 3 is 9, so we have 9 factorial in the denominator, we write that out. 9 times 8 times 7 times 6, all the way to times 2 times 1. The 12 factorial we write out in the numerator, and we can see that the 9 times 8 times 7 times 6, all the way down to 2 times 1, cancels in both the top and the bottom. We're left with 12 times 11 times 10, which equals 1,320. The formula for computing combinations is written C parentheses n comma r parentheses. If we choose r objects from a set of n objects, we say that we are forming a combination of n objects taken r at a time. The notation C parentheses n comma r denotes the number of such combinations. Also, the combinations of n choose r is the permutations of n choose r divided by the r factorial. That is n factorial divided by what's now r factorial times the quantity n minus r factorial in the denominator. Example, how many 3-element sets can be chosen from a set of 5 objects? Order is not important, so it is clear this is a combination problem. In permutation, order matters. That's lining up objects in a row. In combinations, order doesn't matter. So how many 3-element sets can be chosen from a set of 5 objects? With order not important, it's clear that this is a combination problem. So we have a combination of 5 choose 3, or 5 factorial divided by 3 factorial times in the denominator, still the quantity 5 minus 3 factorial. They've written out the quantities, canceled, and then are left with 5 times 4 divided by 2 times 1, which is 10. There's 10 combinations. How many 4-person committees can be formed from a set of 10 people? Order is not important, so this is a combination problem. There are no distinct roles for these people. There's no president, vice president, treasurer. It's a 4-person committee, everyone's equal. So we have a combination 10 choose 4 situation, which is 10 factorial divided by 4 factorial, also divided by 10 minus 4 quantity factorial. They expand the factorial notations and divide, getting to 10. A syndicate has $15 million to spend on tickets for a lottery. Tickets cost $1 and contain a combination of 6 numbers from 1 to 44. Does the syndicate have enough money to buy enough tickets to be guaranteed a winner? The solution: the combination of 6 numbers from 44 possible gives the number of different tickets. That is combination 44 choose 6 is 7,059,052. Thus, the syndicate has more than enough money to buy enough tickets to be guaranteed a winner. Because they have 15 million, but we only got up to 7. In the game of poker, 5 cards are drawn from a standard 52 card deck. How many different poker hands are possible? This is a combination 52 choose 5 question because order doesn't matter. When you're given 5 cards, you rearrange them in your hand, often from lowest to highest to lowest. Maybe you group your pairs, right? But you rearrange your cards often, and that's the same hand of cards, the same hand. So this is a combination 52 choose 5, which is 52 factorial divided by 5 factorial, also divided by 52 minus 5 factorial, which is 47 factorial, for a total of 2,598,960 possible poker hands. In the game of bridge, a hand consists of 13 cards from a standard 52 card deck. How many different bridge hands are there? Egads. Combination of 52 choose 13, which is 52 factorial divided by 13 factorial, also divided by the 52 minus 13 factorial, is a lot. 635 billion, 13,559,600. Ooh wee. 2 men and 2 women from a firm will attend a conference. If the firm has 10 men and 9 women, how many different ways can the conference attendees be selected? The answer is not 19 choose 4, since the answer is not the combination of 19 choose 4, since this includes options like 4 men and no women being sent to the conference. We want 2 men and 2 women. So first we have to select 2 women from the 9 available and then select 2 men from the 10 available. And we could have done that in either order, which is also a combination. Combination 9 choose 2 is 9 factorial divided by 2 factorial, also divided by 7 factorial, which is 36 ways to choose the women. And the combination of 10 choose 2 is 10 factorial divided by 2 factorial, also divided by 8 factorial, which is 45 ways to choose the men. Thus, choosing the women and then choosing the men can be done in 36 times 45 ways, which is 1,620 ways. We're a 16-member consortium wishes to choose a committee consisting of a president, a vice president, and 3 members, and a 3-member executive board. And how many different ways can this committee be formed? We will count this in 2 stages, choosing a president and a vice president from the consortium, and then choosing an executive board from the remaining members. Choosing the president and vice president can be done in the permutation of 16 choose 2 ways because there are distinct roles. And selecting the executive board can be done in a combination of 14 choose 3 ways because we've chosen 2 people already. So the number we have to choose from is down to 14, and we are choosing 3. And it's a combination because there are no distinct roles. There's not a president and vice president like there were in stage 1. So the total is to multiply the permutation of 16 choose 2 times the combination of 14 choose 3. Choose a president and a vice president from 6 people. Choose a committee of 3 members from the remaining 14 people. This can be done in 87,360 ways. Now we're going to look at Pascal's triangle. In Pascal's triangle, we start our labeling of rows with row 0. And row 0 is just the number 1 at the peak of this triangle. And as you go down the sides of the triangle, you're always starting and ending with the number 1. So the second row is written in spaces around the first number. So if you imagine a space to the left and a space to the right of the original 1 in row 0, then below those spaces to the left and the right, we write below that the start of the new line, which is 1, and the end of the new line, which is 1. Now imagine a space to the left of the second row's number 1, and in between the two ones, and then to the right of the second one. In those 3 box locations, that's where we will write our next row below. So you're always writing your next line between the numbers of the previous line. In row 2, we start with a pattern. So again, we begin and end our row with 1. But in the space that would be located between 2 numbers, you add the 2 numbers. So we start with a 1, but then above our space, we have a 1 and a 1, and those sum to the number 2. And then we end with a 1. In Pascal's row 3, we have a 1 to begin our row. Then we sum the 1 and 2 for a 3, the 2 and 1 for a 3, and then we have a 1 to end our row. In Pascal's row number 4, we have a 1 to begin our row. And then to write the next number, we sum the 1 and 3 to write the 4. We sum the 3 and 3 to write the 6. We sum the 3 and 1 to write the 4. And we end our row with a 1. To write row 5, we start with a 1. We sum the 1 and 4 to make a 5. We sum the 4, 6 to make a 10. We sum the 6, 4 to make a 10. We sum the 4, 1 to make the 5. And then we end our row with a 1. And so what are the next few rows of the Pascal's triangle? We would have, not on the tablet, so it might look funny, but in row 6, we would start with a 1. We would sum our 1 and 5 for a 6. We would sum our 5 and 10 for a 15. We would sum our 10 and 10 for a 20. Our 10 and 5 for a 15. Our 5 and 1 for a 6. And we end with a 1. We can see several patterns here. One, since I have the pen out, is that the row number, well, row 1's not a good example of that. Let's erase that one. Your row number, say 3 here, is your first non-1 digit. So you always know what row you're in, but based on the first non-1 digit that you see. All right, what is this good for? It's good for a few things. In our book, it's good for looking at subsets. Pascal's triangle is good for looking at subsets. So Pascal's triangle counts the subsets of a set. The nth row of Pascal's triangle counts the subsets of various sizes of an n-element set. For example, consider the set 1, 2, 3, 4, and the 4th row of Pascal's triangle, which was 1, 4, 6, 4, 1. In listing out the number of subsets of a 4-element set, we get that we have the null set, right? The empty set, the brackets themselves. We could form the set 1, the set 2, the set 3, the set 4 individually out of elements. We could make a set 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4, making 2-element subsets. We can make 3-element subsets that are 1, 2, 3, 1, 2, 4, 1, 3, 4, 2, 3, 4 out of the set 1, 2, 3, 4. We could also make a set that's just the exact same set of 1, 2, 3, 4. Those are the listed subsets of the set 1, 2, 3, 4, if you remember from chapter 2. And what we have is that we have 1 0-element set, 4 1-element sets, 6 2-element sets, 4 3-element sets, and 1 4-element set. 1, 4, 6, 4, 1. That's the row of Pascal's triangle, the fourth row of Pascal's triangle that helps you see how many subsets there should be from a 4-element set. Pascal's entries of Pascal's triangles as combinations and choose R. The rth entry of the nth row of Pascal's triangle is the combination and choose R. For example, consider the fourth row of Pascal's triangle 1, 4, 6, 4, 1. As we listed out before, the combination of 4 choose 0 was 1. There's one way to pick nothing from 4 things, and that's to pick nothing. There were 4 ways to choose one element from 4. There were 6 ways to choose 2 elements from 4. There were 4 ways to choose 3 elements from 4. And there was 1 way to choose 4 elements from 4. Because again, there's only one way to choose everything from the group, and that's to pick everything. So the combination of 4 choose 0 is 1. Combination 4 choose 1 is 4. Combination 4 choose 2 is 6. Combination 4 choose 3 is 4. Combination 4 choose 4 is 1. Assume that a pharmaceutical company has developed 5 antibiotics and 4 immune system stimulators. In how many ways can we choose a treatment program consisting of 3 antibiotics and 2 immune system stimulators to treat a disease? Use Pascal's triangle to speed up your computations. We will count this in 2 stages, choosing the antibiotic and choosing the immune system stimulator. Stage 1, choosing 3 antibiotics from 5 can be done in combination 5 choose 3 ways. If we look at the 5th row in Pascal's triangle, and again, starting our counting at 0, go to the 3rd entry, which is for us is actually the entry after the 3rd entry because of the 1, which is a 0th element. So in the 3rd element of the 5th row, we see 10 ways to choose 3 antibiotics from 5. Choosing 2 immune system stimulators from 4 can be done in looking at the 4th row, which has the first non-1 number of 4, and looking at the 2nd entry, again, starting our counting at 0. We have our 0th entry is 1, our first entry is 4, because it's our first non-1 entry, and then our second non-1 entry is 6. So combination of 5 choose 3 is a 10 plucked off Pascal's triangle, times the combination of 4 choose 2, which is a 6 plucked off of Pascal's triangle, which is 10 times 6, or 60 ways.